So welcome. So we're going to start our first of two chapters on laws of motion, which is basically Newton's laws. So we're going to start off with talking about the concepts of force, and then we'll introduce formally Newton's laws, and then we'll talk a little bit about inertia, mass, and weight. Now, inertia was basically introduced by Galileo, who was like a generation before Newton. And with those kind of three things in hand, we'll start looking at two situations. One is where, if you look at an object, there's no overall overwhelming force. There may be forces on it, but they're balancing each other. And that's called equilibrium. And then we'll talk about circumstances where we don't have a balance, where there is a net force in some direction. And that is going to cause an acceleration. If you have a net force, you must have an acceleration. If you don't have a net force, you cannot have an acceleration. We tend to link force and motion, and it's force and acceleration that go together. We ignore the fact that we have a resistance force, a frictional force that we're usually working against. So we talk about applied force and motion. Yeah, for a motion on the Earth, we need an applied force because we have friction always counting against us. So we're trying to overcome that. But in the rest of the universe, basically, the vast majority of the universe, if you have a net force, you accelerate. You don't just move, you accelerate. And then we divide, we'll start getting ready for the next section, your next life, which may well involve statics and dynamics. And if you're in equilibrium, you've got statics, and if you're not in equilibrium, you have dynamics. So that's where we're going to go. So concept of force. And this is, if you're anything like me, you kind of you have a little daydream here because it's like, I know what a force is, you're just going to ramble on. But in fact, this is like really, really, really important. Because there's stuff in here that we just don't realize. We think we know what a force is, but often we don't. First of all, we can, broadly speaking, characterize our forces in terms of touching forces and field forces, or contact forces and field forces. And in fact, touching forces would be, touching. Oh, sorry. Yeah, I changed chapters, so I've got to pick my pen out again. Okay, so let's go back. Yeah. So we have touching, that's just a word for, I make physical contact. Pushing, I make physical contact and push away from me. Pulling, I make physical contact and connect. And then in contrast with field forces, which are called like gravity, magnetism, electrostatics. And if you think about it, if I told you that we were going to do an invisible force field in class today, like on Star Trek, you'd go, wow, I do. Invisible. But if I told you we're doing magnetism, you go, I know about magnetism. It's like, that's not sciencey, because I'm used to it. But it is very sciencey. And in fact, things like gravity, magnetism, electrostatics are amazing. If you think about it, if you take an object and you let it go, it is accelerated by the force of gravity. We don't really understand that. I can describe it to 5 decimal places. I can tell you what's going to happen really well. But do I really understand what's going on? This is a piece of plastic. How does it know where the Earth is? It's not got any eyes. It's like, well, okay, there's something communicating with it, telling it where the Earth is. There's no strings here. There's no lane it's got to follow. It's mysteriously moving towards the Earth. The only thing is we've seen it every day of our lives, so we're kind of used to it. But it's like amazing. Albert Einstein would say this is not actually moving towards the Earth. It's just following a space-time line. Particle physicists, they're more interesting, I think. What they say is, this mass contains an inexhaustible supply of particles, and they fire out in all directions. And they interact with the Earth. And the Earth is sending out an inexhaustible supply of particles, and they're interacting with a pen. And they mediate, they go between. And they're what causes the force. And you go, that is the craziest thing I've ever seen. But, you know, I'll give you an example of, we see this. Let's say we have two skateboarders who are going along the sidewalk side by side, and one of them has got a backpack, and he throws the backpack at his buddy who catches it. Can you draw for me on your just take a piece of paper, just your notebook, whatever, and draw for me what happens next? What happens to the path? They're coming along, zoom, zoom, zoom. They're coming along. I didn't mean to do that. Zoom, zoom, zoom. Get away. So they come along, zoom, zoom, zoom. What happens from now on? What happens? I throw the bag at you. Where do I go? You throw the bag at me. We're on skateboards. Okay, it's like quite maneuverable. And hopefully you decided that that's going to be caught, and that guy's going to tend to move in that direction, and that guy's going to move in that direction, yeah? So the backpack was an intermediary particle that caused a repulsive force. Yeah? That's kind of amazing when you think about it, and yet it seems very natural to us. So particle physicists looked at this and said, okay, well, we'll just have a particle that's intermediate between the pen and the Earth, and that's going to give rise to an attractive force. Sometimes it's repulsive. If it's two north poles, it'll be repulsive. If it's two positive charges, it's repulsive. But matter only has positive forces as far as our common experience is concerned. You know, they never run out, ever. And, well, can I have a bucket of these, please? You know, they seem pretty useful. Well, no, I can't get you a bucket of them. So they're going everywhere, but I don't have a bucket of them? Well, no. What are they called? Well, they're called gravitons. Okay. Do you believe it? That's a different question. That's a very different question. It's a model that works. So I believe the model works. But do you literally believe it? I'm not even sure that, you know, I very often think that you are figments of my imagination. And I'm just dreaming this stuff up. So, you know, do I believe that you guys exist? I sometimes wonder about that, you know. While ever the evidence is that you guys exist, then I will treat you as if you exist, because the model works. If I treat you like you don't exist, I get pain and, you know, loneliness. So, you know, but so to some extent, lay people want to know, is this the truth? And engineers and scientists go, it works. Because later on I might have a better truth that gives me a better answer. And if that's the case, I'm going to throw all this away. I'm not tied to this. What I see is what I perceive. It's not necessarily the way things really, really, really are. And that's fine, because that's all we can do. So, but isn't that weird? I mean, this is boring old gravity, and yet we're talking about stuff that's kind of like out there. For me personally, when I was a student, I heard that, and it just gave me a creepy feeling, and I didn't want to go anywhere near it. Just let me do the math, and I'm happy. But I don't really, because I would worry about, is it right or is it not? As I get older, I don't care so much. But so some people get fascinated. The weirder it is, the more they like it. And I think they're pure physicists. They're people who kind of like, they do things because. And I'm not an engineer. I'm not neat enough to be an engineer. I'm not picky enough to be an engineer. My brother is the most boring person you could meet in your life. That guy, man. But he's really picky. And he thinks I'm a real slacker. Because I don't pick one thing and do it all the time. I'm too much of a dilettante, you know. But I'm not that much of a dilettante. I want stuff that makes semiconductors better. That was my big thing. I want to make a better semiconductor. So I was an engineer, but not quite an engineer. An applied physicist. Okay. So we have this idea that we have two, let's take about gravity. We have two objects, a little mass and a big mass, and we have mediating particle. Let's not worry about that. We just know that the mediating particles exist, and that gives rise to two forces, because the moon pulls the earth every bit as the earth pulls the moon, which are equal and opposite. And that really is hard for us to accept. If I hit you, you feel pain, I don't. So surely the force of me on you is more than the force of you on me, or else I would be just as hurt as you are. It's not quite like that. Usually what we cunningly do is we hit people in their sensitive bits, like their nose, that are full of nerves. Or we hit them on their jaw where there's some nerve there where if we do it just right, we can knock them out. You know. But if you're not scared about hitting somebody because it doesn't hurt, hit a wall. Okay, you'll find that, yeah, it hurts your hand to hit something. It's just you're not hurting your hand as much as you're hurting the other person. So there's this tendency. You're driving along in the summertime and you have a log bug hits the front of your car. Your car's not splattered with its guts hanging out. The love bug is. And so the tendency is to think that the love bug had a bigger force on it than the car did. But it turns out that the force of the love bug on the car is exactly the same as the force of the car on the love bug. It's just that because the love bug is small, it really is affected by that force. And because the car is big, it really doesn't notice that force. So mass gets involved. It's not just the force, it's the mass that the force acts on. So that gets involved. So we got to, in a way, we've got to remind ourselves over and over again that our common perception, which is very similar to Aristotle's perception. Aristotle was not a stupid person. He was a very smart person. But he wrote things down the way he saw them. Fair enough. And then he tried to explain them by making stuff up. Now, you know, he was building a model. I suppose as a physicist, I can't argue with that. He was building a model, but a very complicated model. And so Aristotle tends to draw conclusions that are, at best, only true on Earth. And often his models are not good. Whereas along came Galileo. Galileo, I think, hated Aristotle. His whole life seemed to be proving Aristotle was wrong. In astronomy, in mechanics, just doing experiments and saying, oh, look, Aristotle's wrong. Oh, look, Aristotle's wrong. Oh, look, Aristotle's wrong. And then in physics, doing the same thing. And then along came Newton, and Newton basically took this basic understanding and codified it. Newton was the big model builder. Galileo was the big experimenter. Newton was the big model builder. He said, oh, mathematically, these things can... Both were important. So we say forces come in pairs, mediating between two objects. Force is a vector quantity. It has a magnitude and a direction. In a way, fortunately, we'll talk about forces on a number line to begin with. So positive is one direction and negative is the other. Unfortunately, that tends to get us involved in arithmetic, and then later on when we want to talk in 3 dimensions, it's kind of like seems like it gets more confusing. And then if an object has several forces acting on it, the forces combine to give one net force. If you have 4 forces pulling on a billiard ball or a pool ball, it does not become elongated in any noticeable way because of the forces. They don't stretch. It stays as a particle, and that's the way we visualize this thing. So the billiard ball is only aware of a net force, F net. It feels one force. That one force determines its acceleration. That acceleration with its velocity determines its motion. Okay. So a bit of different stuff there. Just to throw a wrench in the works, if you think about it, when I touch something, nothing of my matter is actually touching any of the matter inside the projector. Electrons don't hit electrons. If they do, you're in CERN. The electrostatic forces are so strong the matter never touches the matter. And so on a short range, this is a field force. Me pushing is actually a field force. It's just a short range field force. Gravity is a long range field force, and so on. So in a way, everything is a field force, but colloquially divide these up into these two things. Let's talk about Newton's laws. So along came Newton, and he looked at the work of Galileo and a couple of other people, and he said, you know, what you can say is if there's no net force, then there's no acceleration. So how could we say this? I could say F net is equal to 0. Oh, often what people say is they say the sum of all the forces equals 0. The sum of all the forces is F net. And sometimes I'll even put down the sum of the forces net just to remind myself it's the net force. But really, the sum of the forces means the same as F net. Like your net salary is your wages minus your stoppages, like your taxes. That's your net salary. Your gross salary is everything before stoppages. Your net salary is once you have stoppages taken out. It's the overall. It's the effect. Okay. If I have a different situation where there is a net force, I pull a lot harder than you do, so our book that we're fighting over comes in my direction, then we say the F net, or the sum of the forces, is equal to the mass times the acceleration. And acceleration is a vector, just like a force is a vector, so we have a scalar times a vector. So those two, it's neither either or, isn't it? Some would say it's the same equation. It's just an either or. You can't have both. You're either the sum of the forces equals 0 or the sum of the forces equals ma. In fact, some would say the sum of the forces equals 0 means the sum of the forces equals ma when a equals 0. You know. But you can't have the same. You know, I can't do one sum and then say f equals ma and then do another sum f equals ma on the same system in the same axis. Different axes I can, but not on the same axis. So it's one or the other. And then we have Newton's third law. Newton's third law is, again, it's one of those things where it's like, it's so obvious and yet it's so unobvious. It says, for every action force, there's an equal and opposite reaction force. Which is the action? You just pick. When I push you, you push me. We are equal and opposite in terms of our magnitude and direction. There's no way I can push you if you don't push me. I can't push you unless you resist. If I just go like that and you walk out of the way, I've not pushed you, you've walked out of the way. Yeah. Go home, take a piece of paper, push it as hard as you can. Walk to the wall, do the same thing. Very different outcome, very different forces. This paper will not push back against me, so I cannot push it. The wall will push back as much as you like. So it takes two. Both objects are involved in this. And if I choose to avoid resisting your fist, then your fist will have less force on me. If I decide to headbutt your fist, then the fist will have a bigger force on me. Maybe your fist will have a bigger force on it. But it's that combination. So for every action force, there's an equal and opposite reaction force. So it seems to me we're dealing with acceleration. And we're dealing with net force. Okay, so we need to learn a bit about acceleration. And if we say acceleration, well, what is acceleration? Acceleration equals dv by dt. And v is a vector, so v depends upon mag and direction. That's a vector, isn't it? So I can change that vector by changing the magnitude of my velocity. I speed up, I slow down. Or by changing the direction. Didn't expect that. When I change direction, I am accelerating. That's very unexpected. But it's true. If I have a vector in that direction, I go around a corner. If that is my VI and that is my VF, then I changed my vector. My motion vector changed. VI is not the same as VF. They're the same size. I agree with that, but not the same direction. And so there must be an acceleration involved. Accelerations cause change in velocities. Change in velocities are caused by accelerations. So if I want to recognize, is there an acceleration, I've got to look at my change in speed, I've got to look at my change in direction. And if I do have an acceleration, it could be caused only by a change in speed. I could be going fast and then slow. That's an acceleration. It could be caused only by a change in direction. I could be going at a steady speed but go around a corner. Or it could be caused by both. There's no law says I can't have a little speed and then I speed up going around the corner. And so there's an acceleration caused in that. So change in speed and or a change in direction, yeah, is the indicator of an acceleration. What about net external force? You've got to add things up vectorially. Now here I'm showing it in 2 dimensions, so we know that's positive and that's negative, but what about that? And what we've got to do, F1, F2, F3, either in 2 dimensions I could use components, or in 3 dimensions I could use IJKs, but I've got to add them up vectorially. Yeah. Clearly the answers, if this is 10 newtons in that direction, that's 10 newtons in that direction, and that's 10 newtons in that direction, I think that the answer is going to be like that, isn't it? But that's not going to be 30 newtons, I can tell you that much, yeah? You can see that. You can't just add up the numerical values of the magnitudes because they're not in the right directions. It doesn't work. It's like you running around a track 1 billion times and then saying, I'm in New York. You ran around a track. You didn't go anywhere. Well, I ran 3,000 miles. Yeah, but you didn't went in a circle. The direction matters. It's, you know, it's not just how big, it's what direction. So a lot of this is very easy to slip into Aristotle's thinking. A part of our training in Physics 1 is to break you of that Aristotelian thinking. Because when you're stressed or when you're tired, you'll go back to your basic way of looking. So tests is worst. Test, you will, if you're not careful, you will think in terms of Aristotle. You'll assume there's a friction without thinking there's a friction. You'll have bad ideas. And the way you get rid of it is something that never quite goes away. It's like you've got this chronic illness called Aristotelianism. And we can get it kind of like, you know, mastered, but we get it mastered by constant exercises. I have sleep apnea. You don't need to know this, but I have sleep apnea, and I have a little machine, and it's a pain, but, you know. If I don't use the machine, I'm tired all the time, and I can't remember names or anything. You may think it's not working that well, but, you know, it's much better than it was. But I'm trying to get to the stage where I don't need to have the machine, so I'm trying to lose weight because that will help, but there's exercises, so I've got to practice trying to touch my nose with my tongue. And I've got to do it for like 10 seconds every day for like the rest of my life. And if I do it, apparently it'll get better, maybe it won't, I don't know. I read it on the internet, so, you know, what the heck, you know. I'm also stretching myself so I can be 6 foot by, you know, the end of the year, you know. I don't know. But one thing for sure is if I only do it every now and then, it's not going to work. And if I only do it the night before I go and see the doctor, it's pointless. So if you only try and sort this out the night before a test, you will be thinking like Aristotle. So this is time on task. What I tell students is if you only comb your hair before you go out socializing, it's going to be really painful and it's going to look like you've never combed your hair. So you comb your hair even on the days when you are not going out socializing. You comb your hair. The more you comb your hair, the easier it is and the more controlled it is. So it's that. You gotta practice. The way you'll get master this is not by being intelligent. We're all intelligent. It's not by willing it. We all will it. It's by practicing it. It's like, you know. Okay. So let's run through this. So if there is no net force, then there cannot be an acceleration. There's no way there can be. And if there is no acceleration, there cannot be a change in speed, and there cannot be a change in direction. There's no way I can have a change in speed that kind of balances a change in direction. Oh, you change direction, but you change speed just right, so they cancel out. That never happens. If you have either a change in speed or a change in direction, or both, you have an acceleration. So if there's no acceleration, you cannot have done either. If there is a net force, there must be an acceleration. Not, I'd like there to be, but there must be an acceleration. And so, and this is where it gets a little bit iffy, maybe you had a change in speed, or maybe you had a change in direction. You must have had one or other, though. Or you could have had both. It must be one or the other or both. But something must have changed. So if you can kind of get comfortable with that, then it makes life a lot easier. So a baseball player hits a ball into the outfield. So here's the baseball player hitting the ball into the outfield. If our action force is the Earth's pull on the ball, so force of the Earth on the ball, what is our reaction force? Can you have a go at that? And I'm sorry. It doesn't matter. And here's the trick. What you do is you reverse the names. So if the action force is the pull of the Earth on the ball, the reaction force is the force of the ball on the Earth. Well, I shouldn't have drawn it there, should I? There's my second object, Earth. And there's the pull of the ball on the Earth. So there's my action force as I defined it, and there's my reaction force. We should really not talk about the thrust, weight, and the like. We should talk in terms of the force of the so-and-so and the so-and-so. Two objects. There's always two objects. And we should say which the two objects are and put them in order. So the thrust would be the force of the, if you like, the jet engine on the air. Weight would be the force of the Earth on the bag. But we don't. So, I mean, I try to change everybody's mind and nobody's going to change, so you just got to get used to it. Plane is flying straight and level. So here's my plane. It's flying straight and level. It is cruising. There's a technical term. I'm telling you what it means. With a constant speed. With a constant speed of 150 miles per hour, which is correct. I'm going to actually, I do want to see this. So I'm going to just bear with me. I'm going to say discard. I'll come back to it. And then I want to go down here. Because I do want to see this. Choose. There. It's thinking about it. Yeah. And then let's go back here from beginning. I'll get back to it. Yeah, okay. And here's our thing. So can you answer that bottom question, please? Can you click in and answer that bottom question? Because I want to see what you think. So we're back. So let's have a look and see what people said. Oh, that's why I wanted to see it, because it is pretty spread. So let's have a look and let's see what we think the answer is. So a plane is flying straight and level. So I've got to, sorry. Ink. Do it in black, I think. So cruising at a constant speed of 150 miles an hour. So here's my plane. And it's V. V equals 150 mph. Don't care about the units, it's just units. And it's flying straight and level. Boom, 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 boom. And which is correct? The plane is experiencing a net force horizontally. The answer to that is no, that's not correct. And the reason why that's not correct is because it's cruising at a constant speed. So if it is at a constant speed, it is not accelerating. And if it's not accelerating, it's not got a net force. So that can't be right. There is a force of thrust on it, but there's also a force of air drag on it. So, and how do you know that these two balance? Because you've got a constant speed. If those two don't balance, you have an acceleration. Plane experiences a net force vertically. That's also not true because it's flying straight and level. If the force on the wings was bigger than the weight of the thing, it would accelerate upwards. Wouldn't be straight and level. So that can't be true. Both can't be true because neither one of them's right, so it's neither. So it's D on that one. Okay. So can you see how the language? So if you did not get that right, did you have a picture? Did you draw a little plane? Did you put arrows on it? Because that'll help. You know, what I can have is I can have my weight and I have my lift, and then I have my drag, F drag, then I have my F thrust. So there's my four forces that I can think of, and how do they compare? And that's the game I'm playing. How do they compare in comparison with the motion? It's that link. If there is acceleration, there is a net force in that direction. You can bank on it. And if there's no acceleration, there is no net force in that direction. Car is cruising on a constant speed of 50 miles per hour as it goes around a large circular track. Does it accelerate? Can you ever go that one for me, please? Resume recording. Okay, so we're back. Let's stop this. And let's have a look. Again, a bit of scatter here. Some people mainly B or D, so let's have a look at that. So A, yes. Does it accelerate? Yes, in the direction of travel. Not true. It's constant speed, 50 miles per hour. So when you're down here, that's also going to be 50 mph. So you're not accelerating in the direction of travel. Yes, in the direction. Yes, in the direction in towards the middle of the circle. And that actually is correct. Yes, in the direction away from. That is incorrect. And no, it's not accelerating because it's constant speed. Well, you can also change direction, so that's not correct. So what's going on here? We have a thing called a centripetal acceleration. Now, you may have heard of centrifugal force or centrifugal acceleration. Well, centrifugal force for sure. And I want you to wash your mouth out with soap every time you say that, because it's not a good thing to talk about. I sometimes talk about it. It's very much a confusing aspect, so we try not to talk in terms of centrifugal stuff. I'll talk about it later in some more detail, but the thing we need to talk about is centripetal. Centri, and then petal, like petals of a flower. And what's happening here is, if you think about it, my motion went in, I'm going to botch this explanation because I'm trying to use too many colloquialisms, but my motion went in that direction. Something must have caused this down the page velocity to increase, because I got more and more of a down the page component, and that happens because of an acceleration. You know, so B on that one is the best answer. Oh, here's a diagram with a whole bunch of forces on it and a mass, and it's asking me about what goes on. So can you ever go at that one, please? Okay, so we're back. Let's see what people are saying. Let's stop this. And then we're saying mainly A, smattering of D and E. So let's have a look. Does the object accelerate? Well, let's have a look at this. Let's say the sum of the forces in the y direction equals +2 added to -2, which equals 0 newton. So I just did that, basically. In the parlance of physics, I resolved my forces along the y-axis line. Why is the 3 Newton there and the 5 Newton there not included? Because they're at 90 degrees to that line, and so they have no component along that line. You only have components in a direction that you're not, your force is, your vector is not 90 degrees to. The sum of the forces in the x direction equals plus 5 added to minus 3, which equals plus 2 newtons. Oh, okay. Now, if I want to draw this, I clearly have a mass and I have an acceleration. There's no acceleration in any other direction. I can have components of this acceleration in everything apart from vertical, but there's not, you know, it's 0 and 90 degrees to it. So what I say is, oh, the sum of the forces in the x direction equals ma, because there is an acceleration. So I'm going to say plus 5 added to minus 3 is equal to 1 times a. So a is equal to plus 2 over 1, which equals plus 2 meters per second squared, which is 2 meters to the right. The plus means to the right in the way I decided to call that positive and that negative and that positive and that negative. So the way I approached this was I did a nice diagram with all my forces on, and I picked an axis, and I said the sum of the forces along that axis equals, and I figured out, is it no force or some force? If it's some force, I know sum of the forces equals ma. If it's no force, I can say the sum of the forces equals 0. It's like, you know. And then what I did was I said, let's apply it in the direction where I've got some net force and figure out what the acceleration is. So that was coming in via the force. I could have also said, oh, there's an acceleration, and figured out the forces based on the acceleration. So there's all these things work together. So this would be 2 meters per second squared to the right, which is that. If a student pushes on the wall, action force with 10 newtons, what force does the wall push back? Let's very quickly do this one. So let's have a look at this. Any more? Let's stop it. And let's see what people say. Yeah, solidly C. So action and reaction force, equal and opposite. So if this is pushing with 10 newtons, that must be pushing with 10 newtons. We could say if this is positive 10 newtons, that would be negative 10 newtons if we want to put the signs in there. But the magnitude's the same. If you've never been into the frozen north, this might not carry much weight, but you might have been on soft sand, which could approximate to the same thing. So normally a car tyre pushes on the road with an action force of 100 newtons, and the road pushes back with an action force, with a reaction force of 100 newtons. On an icy day, can the car tyre push with 100 newtons? And most people say, yes, your car's still doing what your car does. And your car is still doing what your car does. But that's like saying, I'm going to hit air with 100 pounds. I can't, because the air won't push back with 100 pounds. I can hit the wall with 100 pounds, and I'll feel that force on my knuckles, but I don't feel the same force when I punch the air. I don't feel the same force. My hand is not having the same force. So just because you do the same thing does not mean to say you have the same outcome. So if the ice is not prepared to push back, then you can't push on the ice. Your wheels can spin as fast as they like, but the fact is you're not pushing. And this is about pushing. So on an icy day, can the car tyre push the road with 100 newtons? Absolutely not. If it could, then road must be pushing back with 100 newtons and you should drive on like normal. But the fact is, because of the frictionless nature of the ice, you cannot get that reaction force, so you cannot apply your action force. You can spin your wheels all you like. Spinning's not pushing. It's only pushing when there's some resistance. It's a very different way of looking than most of us have. It's like, and it's, and like everything else, it's not there just because of a test question. It's there because the way we tend to think is confusing. And we're trying to make things simple. We're trying to get things so we can make steady progress. And this is an important thing. Okay, I'll do this one, you do the next one, okay? So we have a pickup truck. Pushes a car along a straight and level section of 275 at 50 miles per hour. V is equal to 50 mph. Compare the force of the car on the pickup with the force of the, compare the force of the pickup on the car, VP on C, pickup on car, with the force of the car on the pickup. Force of the pickup on the car is less, force of the pickup of the car is equal, force of the pickup on the car is greater. Actually, I lied. Can you do this one for me, please? Pick which one you like out of those guys. Whoa, you guys are fast. We're back, and let's put a stop here. Let's see what people are saying. Mainly B, but you know, not an insignificant part of C. So let's see what the answer is. It turns out that the answer is B, and I can tell you that because Newton's third law. Yeah, the action force equals the reaction force. Pickup on car is the action force. Car on pickup, reaction force. It's a law. Okay. Okay. Pickup truck accelerates a car from 0 to 50. So we're at the beginning of our journey now. So here's our pickup and here's our car. And you know, the car broke down, and so somebody comes along and they put their bumper to bumper, and then you start the pickup's engine and you just increase your speed. And so this is before you get to the steady state. You're basically accelerating, and you're going from 0 to 50, so that's an acceleration. And now I want you to compare the force of the car on the pickup with the force of the pickup on the car, given that there is an acceleration. Sorry, I'm just trying to do two things at once. Okay. Let's pause that. Okay, so let's have a look at this. This is going to say, oh, look at that. Mainly C, a little bit of B, a little bit of A. And the answer is B. The answer is B. The answer is B because it's a law. But we have acceleration. How on earth can we have acceleration? Surely F must equal ma. And it does. Well, if F equals ma and there's an A, then we've got to have one force bigger than the other. We do, but not necessarily the forces we're talking about. And so this is going to be a distinction between an action-reaction pair of forces and net external forces. I'm going to draw this a bit simpler. So this is the pickup and this is the car. And the force of the pickup on the car, F pickup on car, is there. And the force of the car on pickup is there. Agreed? That makes sense? They have nothing to do with your speeding up or slowing down. They're just like action-reaction pair. There's two other action-reaction pairs that are significant for this. There's the force of the pickup on the road, and there's the force of the road on the pickup. After all, if the pickup's not pushing against the road's not pushing against the pickup. That's the friction of the tires. And then there's the force of the air on the car and the force of the car on the air. And the reason why I drove these as blocks is I don't want any confusion about, well, the pickup sticks up higher and all this kind of stuff. I'm just 2 blocks, just make it simple. Now, this system will accelerate. This system will accelerate if there is a net force on the system. Not in the system, but on the system. Net external force, we sometimes call it. There's one of my external forces. There's the other external force. So the sum of the forces is equal to minus FA on C added to plus FR on P. And there's no law says they have to be the same. Newton's third law says that the action-reaction pairs have to be the same, not the external forces have to be the same. And so if the force of the road on the pickup is greater than the air drag, then you will speed up, somewhat slowly, but you'll speed up. If the force of the pickup of the road on the pickup is equal to the air drag, then you will have constant speed. And if the force of the road on the pickup is less than the air drag, you'll slow down. So we've got to distinguish, and this gets confusing. We've got to try and clear in our minds. Am I talking about an action-reaction pair, or am I talking about net external forces? And net external forces to what? I could define the pickup as my system and talk about the external forces on that. And if I did that, that would be one of my external forces, and that would be my external force for that object. If I decided to look, I've lost my pens. Oh well. If I decided to look at this other object, I'd have other ones. So it's important. Again, forces are not trivial. You just got to sort out your thinking so it's clear. I used to give that question when we would hire graduate students to be physics instructors for the general physics labs. We'd have graduate students, and I would give them that question as one of a battery of 20 questions. And it's amazing how many people get that wrong, having gone through physics training. Part of physics training is to make sure you don't get that question wrong. And in fact, I remember the first time I did that question, I'd already gone through this physics training, and to make it even worse, I knew I was getting it wrong. My gut was out, my head was telling me one thing, and my gut was telling me something else. So my physics intuition was saying, you're walking off a cliff. And yet my brain kept saying, no, it must be, it must be, it must be. Because I had not resolved my thoughts about what is a action-reaction pair and what is a net external force or external forces. So don't feel bad if you got it wrong, but resolve to sort it out and get it right. By not getting it right, there's confused thinking, which means you're more likely to make mistakes. By taking the effort and getting it right, you're going to resolve things. Physics does tend to get easier the more you master it. You shouldn't aim for surviving. I aimed for surviving and I survived. I should have aimed for mastery. And, you know, as well as Albert Einstein, I doubt it very much. You know, I can assure you it wouldn't be as good as Albert Einstein, but it would have been better than I did trying to survive it. And the irony is it would have been easier all the way through. So the stronger your foundations, the easier it gets. The fewer times you say, it's not going to come up on the test. The more you sweat the detail, especially at the beginning, the easier it gets towards the end. So you're building a foundation, so build it good and strong. It's not the night before the test you put the effort in. It's the night after the test you put the effort in. And every night after that. It's like you really, it's practice. It's every sports person knows this. Every musician knows this. You don't wait for the night before a recital to practice the piece. You do it every night. Same with this. Okay, then a little bit of a side. So we have good old Newton. So Newton was messing with objects of various masses and looking at their motion. And what he found was that if you had more mass, you had less change in speed, which is basically more inertia. Well, less acceleration, that's for sure, which is more inertia. So mass is a measure of inertia. Inertia is my reluctance to change my state of motion. It's my reluctance to accelerate. We use it colloquially. We talk about this party has the inertia. My dad used to tell me I suffered from inertia because when I was awake, he couldn't get me to go to sleep. And when I was asleep, he couldn't get me to wake up. Whatever state I was in, I wanted to stay in for as long as possible. So it was Galileo who came across this idea of inertia, and he named it and all that. Given that F equals ma, we see that mass acts to reduce the acceleration. Bigger m, smaller a. That makes sense. If an object has more mass, it has more reluctance to accelerate. It is said to have more inertia. So a given net external force will cause less acceleration on a bigger mass. And this can have interesting consequences. And we kind of intuitively feel some of this stuff. Another thing I want to talk about is weight and force, because people get these two guys mixed up, in part because in the imperial system, we use weight for like everything. We use pounds for everything, and it's not good. So really, we talk about a Newton, which is a force, and we talk about a kilogram, which is a mass. So we don't have a weighing machine unless it's calibrated in newtons. If we have a machine that's calibrated in kilograms, it's a massing machine. And we don't weigh the block if its answer is going to be in kilograms. We mass the block because the answer is going to be in kilograms. And as physicists and engineers, we try to be very clear about the difference because it'll make a huge difference to our answers. So we say weight's magnitude changes depending upon the gravitational strength and the location in space. I can take a 1 kilogram mass, which is 10 newtons, and take it to the moon, and it's still 1 kilogram, but it's 1.6 newtons. I can take it to interstellar space, and it's 1 kilogram mass, and it's no newtons, because there's no force on it. So the force, the weight, is completely arbitrary, depending upon, well, it's not arbitrary, it depends upon my gravitational field at that location. At the Earth's surface, the gravitational field strength is 10 newtons per kilogram. This means 1 kilogram mass has a 10 newton weight. An apple weighs about 1 newton. So when you want to think about a newton, think about an apple. Hold it in your hand. That's about 1 newton. It's not much. The moon has a gravitational field strength of about 1.6 newtons per kilogram. So a kilogram mass, the same kilogram mass that we had on Earth that weighed 10 newtons, now only weighs 1.6 newtons. And the relationship is Fg, which we often call W, is equal to mg. Yeah. Later on, we're going to do Fe is equal to Q times E, and that is one of your equations in electrostatics. And people find this the strangest equation, and yet they're very comfortable with that, and yet they're really the same thing. Got to keep an eye on the clock. I'm going to stop there. And we're going to take a break. Okay. Let's do a 5-minute break. And then we'll come back and we'll apply these things to real-world problems. So. No, let's do that.